everyone, welcome back to Science Exam Review. Today we're going to be starting off with chemistry, and what better place to do some chemistry learning than in the kitchen? Now, first we're going to start off with physical changes. Here we have an ordinary glass of water. The kettle water is only a little bit warm. Okay, now what can we do to this water to change it physically? Well, pretty much anything we can sense with our 5 senses can change it physically. Color is a physical change. It's green, but it's still water. Shape is a physical change. If I pour this water into a different container, the shape changes, but it's still the same water. So I like to think of ductility as a rubber band. Nothing about the rubber band is changing except for the shape. And that's kind of, again, the same as the shape, but ductility is also a physical characteristic. Now let's toss this thing in the freezer and see what happens to it. Happy physical changing! So as you can see here, nothing about the water has changed except for the state of matter that it's in. State of matter is a physical property. Okay, now how do we test for viscosity? Well, I have a little experiment. Here is a glass. Here is some honey. Honey is a very viscous liquid, as you can tell, because it's not pouring out. So we're going to pour some honey in a glass and see how it's still very viscous. Oh my god, that's the leftover water. See how it's still very viscous? Now, we're going to put it in the microwave for a second. Okay, it's in there. Okay, so I might have microwaved it too much, but as you can see, if I swirl it around a little bit, the honey is much less viscous than it was before. So we changed the viscosity of the honey without changing the honey itself. That's what makes it a physical property. Now, without setting my kitchen on fire or exploding it somehow, I can't really experiment with a chemical change, so I'm going to try and show you the best I can. Flammability is a chemical property because it shows the substance and its reaction with oxygen. Burning something is a chemical change because the wick will never be the same after getting burnt. A little bit of it is withering away and charring up, like with this wick. Atoms within the wick have chemically changed. Now let's get this out of here before I burn my house down. Die, flame, die! Now let's show a nice little chemical change with reactivity. Now usually it means things like potassium and water being reactive. But today I'm going to be using baking powder and vinegar. I know it's supposed to be baking soda, but I don't have any baking soda, and I asked my Alexa if this would still work, and it said yes, so let's hope. Yep, it's fizzing up. See? Now, both of these things have changed chemically to create something else with this reaction. Neither the baking powder or the vinegar is the same after this reaction, and that's why reactivity is a chemical property and change. This is potassium. Now, this is the number of what's called protons. Now, to get the number of electrons, we're going to take this 39, and we're going to subtract a 19 from it, and that equals 20. Now, once we've done all those cool equations, we're going to come over here and we're going to start drawing. So first we draw our little nucleus, and there's the little nucleus symbol, there's a little thingamajig symbol, what the frig? Okay, there's a little proton symbol, there's a little neutron symbol. Now there are 19 neutrons, and there is 20 neutrons. Now our first layer is only allowed to have 2 electrons. And how many are we going to put on this one, my friend? Well, we're going to put 1, 2, 3, 4, 5, 6, 7, 8, giving us a total of 10. But we still need one more ring to get us to our 19. So now we're going to put 1, 2, 3, 4, 5, 6, 7, 8. And now we're at 18. And we'll just make one more big circle around. Oh my god, that's a bad circle. Then we're going to make one more big circle around. And then we have our 19th, which is our valence electron. Now, I'm going to label it to teach you about all the parts of an atom. Now, potassium is in period 1. That's why it only has 1 valence electron. Now, because potassium is in group 1, it has 1 valence electron. And the valence electrons are always found on the outside of the Bohr-Rutherford diagram. Now, when we look at the Bohr-Rutherford diagram, what looks like it's taking up the most space on the paper? Is it the neutrons, the protons, or all these electrons. That's right, it's the electrons. That's why they take up the most volume in an atom. What takes up the most mass? Well, the neutrons and the protons added up are worth more than all of these protons. So, the mass would be them. And the weight and the number of neutrons and protons added up is always going to be more than the number of electrons added up. That's why the neutrons and protons take up most of the mass in an atom. Now, Rutherford and Bohr both made this complex diagram. Do you want to see what John Dalton made? And that's it. That is an atom to John Dalton. And you know what? It kind of looks like a billiard ball. That's why we call it the billiard ball diagram. J.J. Thomson knew a little bit more about, a little bit more about atoms than circle. So he made the chocolate chip cookie, or what nerds like to call the electrons in plum pudding model. So he basically just took something like lithium, and he was like, yes, that is true. There are electrons in atoms, but he didn't know where they were, so he just kind of put them randomly in there. And, you know, it kind of looks like a nice little chocolate chip cookie. That was a bad drawing of one, but still. Now we know about John Dalton's billiard ball, J.J. Thomson's chocolate chip cookie with electron chocolate chips, Ernest Rutherford's... That's the one we don't know about. So Ernest Rutherford basically said, yes, there's one big fat proton in the middle of an atom, and there's just some electrons orbiting around it, like planets orbiting the sun. And then, the reason it's called a Bohr-Rutherford diagram is because Niels Bohr took this, and he decided, no, there's some order to this. So he said that there is actually neutrons and protons in the center, and the electrons orbit it like this. You can see how they look similar, but this one has neutrons. This is a periodic table, and these are the different parts of a periodic table. This whole blue area here is metals, except for freaking hydrogen because it wanted to be different. These are non-metals, and also hydrogen is a non-metal because it wanted to be different. Freaking hydrogen. And these are metalloids. Metalloids can be found in a staircase type pattern, with non-metals being on this side, with helium being an obvious non-metal so you can tell, and all the metals being on this side. Except, anyway, now it's time to go over the properties of metals, metalloids, and non-metals. Welcome back to the lab. Now we'll be testing the properties of metals, non-metals, and metalloids. Now our first test is going to be heat conductivity. We have a metal spoon, a silicone little skincare facial pot thing, and air. Let's see how they conduct heat with this boiling water. First going in is the metal spoon. Next, I'm going to move that aside and take the lid of the pot. It's still silicone, so let's put it in. And let's open up this bag of air. Okay, let's put it in. Okay, now we wait. The first one that we are going to test the heat on is this metal spoon, and you can obviously see that it's steaming. Now let's touch the spoon. Oh, it's pretty hot. Okay, now let's get this thing out. Silicone is only a little bit warm. And the air did not conduct the heat at all. So on the heat conductivity scale, we have metal doing good, metalloids doing intermediate, and non-metals doing low. Next up, we have shininess. This is the metal spoon. Very shiny. This is the silicone lid. Not really shiny. This is the air. Not really shiny. So now on the luster scale, metal is shiny, metalloids are dull, but sometimes can be a bit shiny, and non-metals are dull. Now, malleability and ductility. Malleability is basically if you can change the shape of an object. So, let's test it on this metal spoon. Pretty malleable. And I would test the ductility, but I'm not strong enough to rip apart this spoon. Just know that it is ductile because it is a metal. Metalloid isn't very malleable because you can't really change the shape. And it's not really ductile because you can't stretch it out. And let's test it with the air. No. As you can see, metals are very ductile. Metalloids are not, and non-metals are definitely not. And I had another scientist test the electrical conductivity because I was not going to electrocute myself. So metals conductivity is good. Sometimes metalloids can be conductive, while sometimes they aren't. And nonmetals are really bad conductors. They are not conductive at all. Another important thing to know about metals and nonmetals is that a lot of nonmetals are actually gases, and a lot of metals are actually just solids, making it easier to determine what is a metal and what is a nonmetal. Overall, the winner is metal! So you'd think these are all the groups in the periodic table. Aw, so nice. But no, there's more! So now we know that these rows going up and down are called periods, while these rows going side to side are called groups. Now, every period, at least on the outer edges, has a little family. Okay, forget every time I call these things periods, they're actually groups. So this group 1, is alkali metals, group 2, alkaline earth metals, group 17, halogens, group 18 is noble gas. And they all have specific characteristics that I will explain later.
So alkali metals are extremely reactive and will lose one valence electron to gain a full octet very easily. They're also usually very soft with low melting points and low densities. Alkaline earth metals are also highly reactive. They're also harder, more lustrous, have higher densities and melting points than the alkali metals. Halogens have 7 valence electrons, making them highly reactive. This family is highly toxic and volatile. Noble gases are non-reactive. They're usually colorless, odorless, and have low melting points.
And to test whether we know our groups and periods, let's see if we can find something in group 2, period 3. Now remember, groups are going up and down, periods are going side to side. So group 2, period 3. This is group 1, this is group 2, period 1, period 2, period 3. Group 2, period 3 would be magnesium. Now let's see if you guys can find what's in group 16, period 4. Selenium. Like and subscribe if you got selenium. Whoa, what is that? What does that mean? Well, that means that there are 2 magnesium, 1, what was that one again? Nitrogen, and 3 oxygen atoms in this compound. This is how we show when there are many different atoms in a compound, and how many different kinds of atoms there are of each. What I said probably doesn't make sense at all, but you can kind of see what I'm going for. Magnesium with a little number 2, nitrogen, there's only 1 letter, so it's got to be automatically 1, and oxygen with a little number 3 beside it. You can tell that there's 2 magnesium, 1 nitrogen, and 3 oxygen. Now if you can answer this one, I'll be very proud of you. Now, if you said that there was 1 beryllium atom, 2 nitrogen atoms, and 6 oxygen atoms, then you would be correct. If you guessed anything else, then I don't know what to say, man. Compounds can either be ionic or molecular, and I'll show you what that means. Ionic compounds are when a metal and a nonmetal transfer valence electrons to get a full octet. But what is an octet, you might be asking? Now, argon is an example of an element with a full octet, and that's why it's a noble gas, because it's not trying to interact with any other elements to get a full octet, so it's not very reactive. An octet is when an element has 8 valence electrons, which means 8 electrons on the outer shell. You can remember the word octet because if you think of octopus, they have 8 legs, and an octet is when an element has 8 valence electrons. Now, back to ionic compounds. Sodium chloride is an example of an ionic compound because it combines a metal and a nonmetal. Now, here is a Lewis dot diagram of sodium and a Lewis dot diagram of chlorine. The sodium needs to get rid of 1 valence electron to get a full octet, and the chlorine needs to gain 1 valence electron to get a full octet. So, when sodium finds chlorine, sodium gives that valence electron to chlorine, and now chlorine has a full octet. And sodium has a full octet. So now the sodium is positively charged, and the chlorine is negatively charged, because it's gained a negative electron. This is how I remember which is which. Cats are nice. Cats are positive. Cat ions are positive. Anions, however, I just added T. Now it's antions. Ants are bad. Ants get all over your food and make it dirty and gross. So, anions are negative. Now, a molecular compound is a nonmetal plus another nonmetal. And an example of a molecular compound is water. Hydrogen plus 2 oxygens is a molecular compound. To get a stable octet, instead of giving away electrons, molecular compounds share them. Also, it's important to note that metals form cations, while nonmetals form antions. For density calculations, please review that in a different YouTube video. I don't think I'm the right person to explain that. And that's all I remember of chemistry. Remember, kids, matter cannot be created or destroyed. Tune in next time for electricity, or as my science teacher likes to call, physics.